Hello everyone, welcome to this webinar from METTLER TOLEDO AutoChem. My name is John Good and I am a Technical Applications Consultant. Today's webinar topic is the application of quantitative analysis to predict absolute concentration information in real time. During this presentation I will provide a brief introduction to the React-IR technology before establishing the differences between qualitative and quantitative data analysis. I will introduce some of the key requirements for developing a quantitative model and focus on strategies that produce the best results for the desired outcome. The key differences between a simple univariate model and a more complex multivariate model will be outlined, and finally I will illustrate these two modeling techniques by discussing their application to some real-time in situ FTIR production data. To do this I will use the IC-Quant software tool to illustrate the development and use of these two types of calibration models. We'll finish the webinar with your questions. Firstly, let us discuss React-IR. React-IR is a real-time, in-situ, mid-infrared system which measures specific fundamental absorptions of individual reaction components. Essentially, the React-IR provides a molecular video of the reaction, or in other words, allows you to follow the making and breaking of chemical bonds. The advantages of using the React-IR are that variations in reaction kinetics, selectivity, reactivity, and endpoint can be detected in real time, without having to take subsamples. Because the React-IR is an in-situ tool, the analysis can be undertaken in a wide variety of reaction conditions and can measure toxic, hazardous, or explosive substances along with air and water-sensitive reactions. Traditionally, React-IR analysis has been qualitative in nature. This is where the relative concentrations are sufficient to monitor the reaction, for example to determine reaction initiation or intermediate formation. However, the ability to take this a step further and predict absolute concentration is sometimes useful or essential, especially for monitoring and controlling continuous processes and during production, where an accurate reaction endpoint determination can significantly improve the product quality and yield. Traditionally, if an absolute concentration is required, an offline analysis of a manually collected sample is performed. The collection of a manual sample often has safety implications, and there is a requirement to quench or cool the sample to ensure that it does not continue to react. Additionally, the results of the offline analysis are very often delayed. With real-time in-situ quantitative monitoring, however, these issues can be completely overcome. The foundation of all spectroscopic quantitative analysis is the Beer-Lambert law, or Beer's law. This law describes the linear relationship between absorbance and the concentration of an absorbing species. Beer's law basically states that the measured absorbance A is equal to epsilon multiplied by B multiplied by C, where epsilon is the wavelength-dependent absorptivity coefficient, which is a property of the molecule or a specific functional group within the molecule, B is the path length, and C is the concentration. The React-IR probe design uses ATR, or attenuated total reflectance, which means that the path length of the IR light within the reaction mixture is fixed due to the probe having a fixed number of reflections within the ATR crystal, as can be seen in the schematic on the left. Combining this with the fact that the absorptivity coefficient is a property of the molecule results in the absorbance being proportional to concentration. Therefore, it is possible to develop a quantitative model that correlates the changes in reaction composition, i.e. concentration, with changes in infrared data, i.e. absorbance value, and allows the concentration of key reactants, products and byproducts to be determined in real time. Although Beer's law is fundamental to the development of a quantitative model, calibration design is also central to a robust model. And there are four key steps that are important in the development of a calibration model. Firstly, determine which component or components you wish to model, for example reagent or product, along with the goal of the model, such as endpoint determination. Secondly, select the standards, either reaction or synthetically prepared standards, along with the distribution of these standards for the goal of the calibration model. Thirdly, determine independently the concentration of the component of interest for each reaction standard, for example by HPLC or GC analysis, or gravimetrically for synthetic standards. Finally, measure high-quality IR spectra of each standard. Once these steps have been taken, a quantitative modeling software package, such as IC-Quant, can be used to develop the required quantitative model. However, prior to this, I want to discuss each of these steps in a little more detail. Two reaction profiles are displayed in this slide, below which I have provided examples of potential distributions of standards. Defining the monitoring goal very often determines the required distribution of standards. Low accuracy and precision will generally result when the selection of standards broadly covers the entire reaction. it is much better to define the goals such as initial charge ratio or endpoint determination, and then select the appropriate distribution of standards required to achieve this goal. If you want to monitor the complete reaction, it is better to have a single calibration model for each monitoring stage. As shown, the best design will always bracket the concentration range of the key component, and it is important, especially if you're using reaction standards, to collect manual samples that are evenly distributed over the calibration range of interest, as shown. The primary intention of this slide is to show the criteria used to decide which type of standards to use to develop the calibration model. Although synthetic standards are the best option for high accuracy and precision for simple reaction mixtures, they are not always practical. Reaction chemistry is characteristically dynamic, and therefore preparing standards of a reaction mixture is difficult due to the non-availability of some of the components of the mixture, along with the potential presence of byproducts and impurities. Additionally, preparing synthetic standards followed by infrared measurements is both time-consuming and costly, especially when temperature modeling is necessary. Reaction standards are therefore generally an easier option, as only a reference method is required to determine the concentration of the components of interest. The accuracy of this reference method generally provides a good indication of the accuracy of the final quantitative model. The one drawback to using reaction standards is that it is often necessary for the reaction samples to be quenched or cooled to ensure that the sample does not continue to react or change prior to offline analysis. It is best to collect reaction standards over several weeks or several batches rather than days in order to model the natural variability in the process. Ideally, the number of standards should be at least 3 times the total number of components, including temperature if that is changing during the reaction. If it is a batch process, then it is recommended that you collect data from as many batches as possible. Ideally, the variation of the component concentrations within the standards should be random, and therefore each standard should be mutually independent. This generally only becomes a problem when preparing synthetic reference standards, as serial dilution cannot be used. Ideally, an even distribution of standards over the concentration range of interest is beneficial. This very often requires planning as to when manual samples should be collected from the reaction. Typically, methods predict poorly outside the concentration range of the model, but if you do wish to accurately predict outside the nominal concentration range, extra standards should be included in the calibration model that have concentration values outside this range. Having discussed the goals of the model and the collection and analysis of the reaction standards, I would now like to discuss the development of the calibration model itself. The calibration model acts as a transfer function, with the infrared spectrum as its input and predictions of the desired component concentrations as its output. There are many different regression algorithms that provide a method of correlating spectral data to constituent concentrations, and I am going to discuss 2 of these, univariate and multivariate. These use very different algorithms. The univariate is a simple classical least squares algorithm, using peak height or peak area, whereas the multivariate algorithm is a partial least squares algorithm. Other than the specifics of the algorithm, the biggest differences between these two is in how much of the infrared data is used in the model. A univariate model generally uses a single wave number for each component, whereas a multivariate model generally uses a much larger wave number range. Additionally, a multivariate model can cope with overlapping bands and temperature variations, whereas a univariate model cannot. Unfortunately, I do not have the time to go into the theory behind each of these in any detail, but hope that you will get a flavour of the advantages and disadvantages of each method. There are many other types of algorithms such as inverse least squares and principal component analysis, which I also will not be covering today. A univariate model, as I have described, is a simple model that generally uses a single wave number measurement from the infrared spectrum to model the component of interest. This therefore means that the component of interest needs to have an isolated band within the infrared spectrum of the reaction mixture. A simple calculation using peak height or peak area provides an absorbance value that can be compared to the known concentration of the sample, as shown in the top right-hand figure. The univariate model then simply calculates a correlation factor K between the known absorbance values A and the known concentration C. This is achieved by minimizing the least squares errors at the calibration points, as shown in the bottom right-hand figure. Univariate models are generally easier to develop and interpret, as I will show you in the example application. However, they are limited. In the case of infrared models, they only use a very small amount of the spectral information, one wave number out of approximately 400. Additionally, these models cannot deal with interferences or overlapping bands, and cannot take temperature variations or intermolecular interactions such as hydrogen bonding into account. Finally, the predicted unknowns must be mixtures of exactly the same constituents as the reference standards. A multivariate model is a more powerful model that uses more of the available infrared data, i.e. a spectral region rather than a single wave number. This is one of the reasons why I can deal with overlapping spectral data and reaction temperature variations. Although a multivariate model is much more powerful than a univariate model, the underlying partial least squares algorithm is more complex. It is basically a type of factor analysis which reduces the complexity of the dataset, but which has many more diagnostic tools to determine the optimum number of factors. In simplistic terms, these factors are the number of independent variables required to describe the dataset, which in our case is the number of individual components in the reaction mixture, along with other changing variables such as temperature. I do not plan to cover the theory of PLS and factors in any more detail, as it would require another webinar, but I do intend to cover the steps required to develop a multivariate model to give you an understanding of the process and when it is applicable. I would now like to go through an example application where the data we are using was collected using the Monarch production FTIR system using a K4 conduit, a sentinel probe and a recirculation loop. The reaction step we are looking at here is the conversion of a ketone to a secondary amine, and the goal of the calibration model was to determine the reaction endpoint by quantifying the residual ketone. The reason for developing a quantitative model in this case was that if the reaction is allowed to go beyond the endpoint, the impurity concentration increases, which reduces the yield. For this application, the reaction is performed at reflux, so we have a constant reaction temperature. The top plot in this slide contains 8 overlaid infrared spectra selected from data measured throughout a 12-hour batch. It is immediately clear that there are several isolated bands, such as the bands at 1044 and 903 wave numbers, that are decreasing in intensity as a function of time, and could therefore be potentially used to generate a univariate model. In this case, manual samples were also collected approximately every hour throughout the reaction and analyzed by HPLC. To try and find out whether a univariate model would work with this infrared dataset, we have plotted the intensity or height of both of these peaks as a function of time and compared the resulting trends against the trend created using the HPLC values from the manual samples. The blue curve in the lower plot shows the peak height of the 903 wave number band, plotted as a function of time, whereas the red curve is the HPLC trended data. Correlating these two trends within the ICIR software showed an excellent correlation of 0.988 for the 903 wave number band and a slightly lower correlation of 0.981 for the 1044 wave number band. It was decided in this case to use the most intense band since we're looking at an endpoint model and good signal to noise is important. For this application, we are interested in quantifying the residual ketone, so there is only a need to model the last 6 hours of the reaction as indicated. To develop a univariate model for this dataset, we will use the IC-Quant Univariate Modeling package within the ICIR software, which is one of several data-to-information modules currently available within the IC software suite. Unfortunately, I don't have time to go through each of the steps in detail, so I will summarize the basic procedure in the following 2 slides. Prior to developing any quantitative model, the experiment files for the 4 batches that we are using to develop this model were opened and the quality of the spectral data checked. This is an important step as you don't want poor quality data, spectral or reference, to be included in your model, as this will reduce the accuracy of your model. The individual IR spectra measured at the same time as the manual samples were collected are pinned so that they can easily be brought into the model. The screenshot shows the basic univariate model page with the Add Spectra dialog box. This contains a list of all the open experiment files, which you can see as tabs along the top, and within them the pinned spectra. It should be noted at this point that after developing a model, additional spectra from new batches can always be added at any future date. After selecting the spectra to be used in the model, they are listed in the model data pane, as shown in the left-hand side of the screenshot. Initially, no data is displayed in the results pane in the top right-hand corner, as additional information needs to be entered in order for a model to be generated. The HPLC reference values for the ketone are entered into the model data pane for each IR spectrum selected for the model. If necessary, individual standards can be made inactive within the model by unchecking the box to the left of the spectrum file name. Once reference values have been entered, an IR peak needs to be selected using the spectral viewer in the bottom right hand corner, just as you would do when trending a peak in ICIR. In this case, we have selected the peak at 903 wave numbers, and we are using a simple peak height analysis. Once a peak has been defined, the model will be automatically calculated and the results displayed in 2 charts, peak versus component as shown here, and a second tab with predicted versus actual. In addition, the regression coefficients will be displayed, the slope, intercept, and the R-squared value, as indicated in the slide. One of the great features of the IC-Quant package is that the effects of data treatments, such as subtracting a solvent spectrum, applying a baseline correction, or a derivative, can be implemented quickly and easily, and the results displayed almost instantaneously. In this case, a second derivative function has been applied to the spectral data, as can be seen in the spectral viewer, and the effect on the regression lines and coefficients are clearly observed. The application of a second derivative to this dataset improved the fit, with the R-squared value increasing from 0.896 to 0.989. This improvement is mainly due to the removal of slight baseline changes between the individual batches. Looking at the differences between the predicted and true values, it was determined that the model accuracy was sufficient for the application, and the model was therefore saved. Prior to implementing a univariate model, it is always recommended to test it on new spectra for which reference data are available, or a complete batch that was not included in the calibration model. In this example, the model was applied within the IC Quant software to a fifth batch, and the predicted results compared against the reference HPLC data for the two manual samples, as can be seen in the table. It is comforting in this case to see that the predicted concentrations for the two reference samples are within 1 to 0.2%, which is in line with the model accuracy. If the accuracy of the predicted samples is not as good as the model, it is an indication that the model is not as robust as we would like, and additional standards should probably be added. In conclusion, therefore, we have shown in this case that a univariate model works well for this application and can be applied to future batches or in real time to determine the optimum point to stop the reaction. One of the major differences between univariate and multivariate modelling is that with multivariate modelling more emphasis is put on validating the model for robustness. To do this, the calibration standards are generally split into two, one of which acts as the calibration or training set, while the other acts as the validation or test set. These data sets contain all the expected components and expected concentration ranges that you are interested in modelling. The purpose of the validation set is to evaluate the model developed using the calibration set, verifying both its robustness and suitability. This data set therefore needs to consist of a set of standards that are independent and were not used in the calibration set, but which span the component and concentration range of the calibration model. Validating a calibration model is one of the most important steps in the development of a multivariate model. The validation process not only provides an indication of the accuracy of the model, but more importantly the optimum number of factors to use to describe the calibration data set without underfitting or overfitting the data. There are two different validation options available: cross-validation using the calibration set and test set validation using the independent validation set. Cross-validation uses a procedure to sequentially remove one of the calibration standards while developing a calibration model with the remaining standards. The calculated model is then used to predict the standard left out, and the procedure repeated for all the standards in the calibration set. This is a reliable method of estimating the model accuracy via the root mean square error of calibration, along with the root mean square error of cross-validation. Additionally, the validation residual variance provides a means of defining the optimum number of factors required to model the data, while maximizing the accuracy of the model. Once the optimum number of factors have been selected, a test set validation can be performed, which provides a true indication of the model accuracy via the root mean square error of prediction. I would now like to go through a second example where the reaction step we are looking at is the conversion of a primary alcohol to an ether. The goal of the calibration model in this case is to determine the reaction endpoint by quantifying the product ether concentration. Again, in this case, the impurity concentration will increase and the yield will be reduced if the reaction is allowed to go beyond the endpoint. In the upper plot, we have overlaid second derivative spectra collected roughly every 2 hours throughout the course of the reaction. The spectral features look fairly well separated, and we know by comparing this spectrum to a reference spectrum of the product that the band at 1480 wave numbers is associated with the product, and as expected is increasing in intensity as a function of time. In principle, this dataset therefore looks like it would be suitable for a univariate model. However, when we overlay the HPLC reference data from manual samples collected throughout the batch, the red trend line in the plot below, with the peak area of the peak at 1480 wave numbers, the blue trend line, we can clearly see that there is a very poor correlation, and that therefore a simple univariate analysis is not appropriate. To develop a multivariate model, we will again use the IC Quant multivariate modeling package within the ICR software. Unfortunately, I don't have time to go through each of the steps in detail, so I will summarize the basic procedure in the following slides. Prior to developing any quantitative model, the experiment files for the 3 batches that we're going to use to develop the model were opened and the quality of the spectral data checked. The individual spectra measured at the same time as the manual samples were collected were pinned so that they can easily be brought into the model. The screenshot shows the basic multivariate model page with the Add Spectra dialog box. As you will note, this looks and functions in a very similar way to that used within the multivariate modeling package. After selecting the spectra from the 3 batches to be used in the model, they are listed in the model data pane on the left-hand side of the displayed screenshot. The selected individual spectra are displayed in the Spectra Viewer pane in the bottom right-hand corner, and by default the spectral region between 900 and 1900 wave numbers is used in the model development. This spectral window can be modified as required, but by default covers the main fingerprint region of the spectrum. Initially, no calibration results are displayed in the Results Viewer pane in the top right-hand corner, as primary values for the component of interest in the model data pane need to be entered. By default, all the spectra selected for the model are assigned as calibration standards. In our case, we wish to define 2 batches as calibration standards and 1 batch as the validation or test set, which we can do by using the radio buttons on the left-hand side. Once these steps have been completed, the Calibrate button can be selected in the Quantitative Analysis toolbox on the right-hand side, which performs both the calibration and the test set validation in a single step. Once the calibration has been performed, 13 different diagnostic charts become available to evaluate the model. These include charts to determine the optimum number of factors required to describe the data, and charts to assess the predicted results of the calibration and validation sets. I have selected 4 of the 13 available charts to display here. The actual versus predicted cross-validation plot in the top left-hand corner of the 4 plots shows the results of the cross-validation procedure, where the predicted results are plotted against the actual concentration values. In this case, the cross-validation procedure has determined that 15 factors are required to describe the calibration data. We know that there are only about 5 components in this reaction mixture, so we are severely overfitting the data with 15 factors. We can also see in the actual versus predicted cross-validation plot that we have included standards in the model that were collected outside the region of interest, which for us is the reaction endpoint. We can therefore remove any calibration standards with concentrations below 60% by selecting the Ignore Radio button next to the individual standards to be removed from the model as shown. After making these changes and recalibrating the model, we see an immediate improvement in the actual versus predicted cross-validation plot, and this is borne out in the number of factors, which has decreased from 15 to 7, and also by the root mean square error of cross-validation, RMSECV, which is reduced from 2.11% to 0.704%. This is a good example of just how important it is to define the goal of the model and to use standards from only the region of interest to get the optimum model performance. The RMSECV versus number of factors plot in the top right-hand corner is a typical example of the type of plot you are looking for. As the number of factors used to describe the data increases, the model error, RMSECV, decreases to a minimum with 7 factors and then increases as you start to overfit the data. The bar chart in the lower right-hand corner shows the Mahalanobis distance for each sample, where the blue bars are for the calibration standards and the green bars are for the test set standards. The Mahalanobis distance, or M distance, describes how similar the individual standards are to the average of all the calibration standards. And this chart shows us that the test set standards are somewhat different in this case to the calibration standards. In order to improve the situation, we can try various spectral data treatments, such as a second derivative. Due to the flexibility of the software, data treatments can be applied and the effect on the model performance assessed quickly. If they are not found to improve the model, they can quickly and easily be removed, much in the same way as you can apply and remove data treatments from experimental data. Applying a second derivative, as can be seen in the Spectra viewer at the bottom of the screenshot, and recalibrating not only significantly improved the M-distance plot in the lower right-hand corner, but also decreased the root mean square error of cross-validation from 0.702% to 0.622%, along with the root mean square error of prediction, RMSEP, for the test set standards, which decreased from 1.47% to 0.28%. The same is true for the F-test statistic, bottom left-hand chart, which is an indication of the spectral residual, which can help to identify false samples or components not present in the calibration set. In this case, the test set standards, the green bars, have a similar residual value to the calibration standards, blue bars. If I was to improve this model in any way, I might think about adding some more standards with concentrations between about 65 and 75%, as we clearly do not have an even distribution of standards, as can be seen in the actual versus predicted cross-validation plot. There are many other diagnostic tools, such as score plots and leverage plots, available to determine the quality of the model and the optimum number of factors to use. Unfortunately, I do not have time to describe all of these in detail. Once a model has been developed, it can be saved and then applied to future batches, either post-process or in real time. In this case, the model was applied within the ICQuant software to a 4th batch, and the predicted ICQuant results shown in green compared to the plotted HPLC data shown in red. The results look very good, but again it is critical to remember that the predictions are only valid for the concentration range over which the model was developed, which in this case is from 65 to 93%. I have also plotted 2 diagnostics for this batch, Mahalanobis distance and F-test, or spectral residual, which are automatically calculated along with the predicted value. These provide additional information regarding the quality of the prediction. Often, although the predicted value looks good, these statistical indicators will start to change in value, provide an indication that something is wrong, such as possibly an increasing concentration of an impurity. In case you were wondering, the reason why the univariate model did not work with this dataset was due to the fact that the temperature changed during the reaction, and also the reaction involved a distillation step. Finally, to summarize, the development of a calibration model, be it a univariate or a multivariate model, involves a number of important steps. These include a consideration of the goal of the calibration model, i.e. what part of the reaction do you want to quantify? Can you collect reaction standards or prepare synthetic standards over the range of interest? And do you have a reference method available for the component or components of interest? These are fundamental to a good calibration model and provide a solid foundation on which to develop the appropriate calibration method. The application of quantitative analysis to predict concentrations in real time provides some unique advantages over a qualitative approach. These include an accurate control of your process, the removal of any safety issues associated with manual sampling, and an almost instantaneous result compared with the more traditional offline approach. It is this that, in my opinion, offers the greatest value. Thank you very much for your time and attention, and now I'd be happy to answer any questions you may have.